chemistry worksheet. So number one, it says the following molecules bromothiamyl blue. Determine the molecular formula, the number of sigma bonds, number of pi bonds, lone pair electrons, and hybridization. So to determine the molecular formula, all you have to do, oops, I didn't erase some stuff here. All you have to do is count everything. So if you go ahead and you count, I'll do all the carbons first. You have, just remember in these line and angle drawings, every vertex is a carbon. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So there's 27 carbons. Typically, we put the H after the number of carbons. So to count all the H's up, you have to remember that the hydrogens are not drawn in these line and angle drawings to carbons. So any carbon where the hydrogens are not drawn, you do have to draw or keep note of them. So like this carbon over here, this methyl group has 3 hydrogens. This one is the same. This one's also the same in that one. They all have 3 hydrogens, and this one. So I want to keep that in mind as I'm counting these. This carbon here, and also I want to note, how do I know they have 3 hydrogens? Carbon wants to have 4 bonds. If you have a neutral, stable molecule, typically in organic chemistry, carbon will have 4 bonds. This is not always true. For those of you who will take organic chemistry in the future, there are things like carbocations, there's carbenes, there's carboanions, there's carbons that don't have 4 bonds total. But for the sake of this class, I don't think there's anything super weird that you're gonna have to worry about. So assume that carbon is gonna have 4 bonds. So if you assume that, this carbon has 1 bond explicitly drawn to another carbon. And then there's 3 hydrogen bonds, or bonds to hydrogen, I should say, that are hidden. This carbon here, this one already has 3 bonds. It has a bond to 3 carbons. It's missing 1, and so it needs a hydrogen drawn in. Same with this carbon over here, right? This carbon is missing a hydrogen. So anywhere on these benzene rings, you want to make sure that you draw in the hydrogen where the carbon is not connected to anything. Or at least keep it in mind as we count. So counting these, we have 3, 6, 9, 12, 15, 18 from all the methyl groups, 19, 20. I think those are the only carbons with the 2 methyls. Yeah, so we're at 20, 21, 22, 23, 24, 25, 26. Now we've counted all the hydrogens on the carbons. We have to count the hydrogens connected to other things. We have 2 hydrogens that are connected to an oxygen, also known as alcohol groups in this case. Or I guess it would technically be a phenol, but we have these OH groups, which give us 2 more, and we get 28. Moving on, we count the number of oxygens. There are 1, 2, 3, 4, 5 oxygens. We should probably do bromine first because alphabetical order, but it doesn't really matter. So bromine, there are 2 bromines. And then for sulfurs, there is 1. And that is it. That is our molecular formula. Now we can move on to the number of sigma bonds. So sigma bonds is the first bond between an atom and another atom, right? So if you have something with tetrahedral hybridization, or we're talking about like carbon here, something with tetrahedral hybridization with carbon has 4 bonds. These 4 single bonds are all sigma bonds. If you have something that has like trigonal planar hybridization, so a carbon connected to 3 things, there's 3 sigma bonds in that. The carbon will have 4 bonds, but that first bond that it makes with something else is the sigma bond. Without getting too much into hybridization and why that is, and stuff like that, the sigma bond, again, you can think of as non-pi bonds or non-pi bond connections. So to count all the sigma bonds here, you can, again, just count them up, right? Every bond between a carbon and another is one sigma bond. So those are a sigma bond, these are sigma bonds. These second bonds in the benzene ring are not sigma bonds, right? Those are pi bonds. The second bond that's made. I'm not going to go ahead and count all these up. You do end up getting, I think it's 38 about when you count them all up without the hydrogens. So make sure you add in the number of hydrogens, count all those bonds as well, and you end up getting 66. An easy way to do it is count all the bonds you see, and then just add the number of hydrogens, because every hydrogen can only make one bond, or it has to be a sigma bond. Moving on, we have pi bonds. The pi bonds are the second and third bonds that you may see between two atoms. So here's one pi bond, right? The second bond here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 pi bonds. Now we can talk about lone pair electrons. So if you draw on the lone pairs here, and we're assuming a neutral formal charge for all of these. Sulfur has something weird going on. It has the expanded octet. We're going to assume there's no electrons on there. So oxygen needs two lone pairs to have a formal charge of 0. Typically wants to be bonded to two things with two lone pairs. Bromines typically want to be bonded to one thing, or halogens, and have 3 lone pairs. We count all these lone pairs up, and you get 16. Now we can talk about hybridization. So I'm going to start with sp3 hybridization. And we're going to differentiate between carbons and oxygens. Now, hybridization, a short way to do hybridization is to look at how many groups that the atom is connected to. So if you have 4 different groups, or 4 electron groups, I should say, it is sp3 hybridized. Electron groups being lone pairs or whatever else. For those of you who take organic chemistry in the future, you may learn things like conjugation. You may learn about oxygen lone pairs being conjugated, and the hybridization may be different than you think. So for this class, based on the answer key, we're going to go ahead and just assume that this is based off of electron groups. So for sp3, you need 4 electron groups, or you can think of this as 0 pi bonds, right? They are equivalent ways of thinking. So if you have 4 groups, there can't be any pi bonds to that atom, right? Because you could count all the atoms with 4 groups, or you can look at all the atoms with no pi bonds. One is a lot easier than the other. We aren't including hydrogens here, right? Because hydrogens don't have a p orbital, so they're not going to be sp3 hybridized. So we're just looking at carbons, oxygens. So for the carbons, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 carbons without pi bonds or connected to 4 things. They are equivalent. 9 carbons. For oxygens, we're looking for oxygens with no pi bonds. We have 1, 2, 3. 3 oxygens have no pi bonds or have 4 unique, or not unique, but 4 electron groups. Technically, if you were to do bromine, using the same logic, it would be both bromines. But that is it for the sp3 hybridization. For sp2 hybridization, You can look at things for 3 electron groups or 1 pi bond, exactly 1 pi bond. I don't want you to think of this as actually when we move on to SP, don't think of it as double bond, think of it as pi bond, number of pi bonds the atom has. So if we're looking at things with 1 pi bond or 3 electron groups, all these carbons in these rings have 1 pi bond. There's 3 of them. So there's 18 carbons, and those are the only carbons with pi bonds, 1 pi bond. Then looking at oxygens, there is 2 oxygens with 1 pi bond. Moving on to sp hybridization, think of this as things with 2 pi bonds. Again, do not think of this as a triple bond because you can have a carbon that looks something like this, right? That has 2 pi bonds. That middle carbon is sp hybridized, but this is not a triple bond. These are 2 double bonds. So things with 2 pi bonds in here is nothing. There's nothing with 2 pi bonds. So that is it for question 1. A lot of counting. Number 2, it says draw the Lewis structure. So I'm going to draw this with the line and angle drawing instead of Lewis structure as it's shown in the key. So it says CH3, CH2, CON. So I like to read it from left to right. CH3 means that we have a methyl group at the end. This carbon right here, right? There's 3 hydrogens that I have not drawn in because I don't have to, based on the line and angle structures. Then we have CH2, which is going to be this carbon down here, the one that the CH3 is connected to. Then we have CON, so this is the carbon. Now, how do you know whether or not this carbon is connected to the oxygen and the nitrogen and the 2 methyl groups, or one of the methyl groups? These parentheses typically mean 2 things. It means that they are stuck onto the same thing, or it indicates a repeating subunit. So as we'll see in B, like a carbon chain. Typically, if it's a methyl group or if it's a CH group, it means they're stuck onto the same thing. If it's a CH2, generally it's a carbon chain just because carbon chains are usually CH2s. So if you, and I want to note that CH3 can't be in a carbon chain, otherwise carbon would have 5 bonds. So the CH3s have to be connected to the same thing. They are on the same thing because of the parentheses. They both can't be connected to the carbon. How do I know? Because this carbon is already connected to the CH2 here, right? This one. It's connected to the oxygen and the nitrogen, right? If I connect 2 more things to it, that's 5 bonds. You can't do that. So the carbon ends up being connected to the oxygen and the nitrogen. It forms a double bond with the oxygen. And then the 2 methyls that stick off of the nitrogen like that. How do you know that the double bond is to the oxygen and not the nitrogen? The CH3s, again, have to go on the same thing. When you draw structures in organic chemistry, you want to minimize the formal charge. So something that you may want to review, something you saw in 2A. Oxygen wants 2 bonds and 2 lone pairs to have a minimum formal charge. If oxygen has a single bond to carbon, then it has the 2 methyl groups. You end up getting a positive formal charge, and then the nitrogen would end up having a -1 formal charge. That's not a very good structure. That's what we often say you want to minimize the charge. So the oxygen gets the double bond, the nitrogen gets the 2 methyl groups. Very common thing in organic chemistry, you will see double bonds to oxygen more than nitrogen, the amine group. Moving on to B, we're doing the same thing here. We're just drawing it out. We have a methyl group. Now these 4 CH2s are not connected to the same thing, right? You can't have 4 CH2 groups connected to the methyl or this N carbon. That would violate the octet rule. So this is what I was saying before. This is going to be a chain of carbons. So I have 1, the CH3 group, one CH2 is down here, 3, oops, 2, 1, 2, 3, 4. So just to double check, make sure I have all the correct carbons. So far, I should have 5 carbons. I have 1, 2, 3, 4, 5. That is correct. And I go down one more for one more carbon. This is going to be the carbon with my double bond like that. And you can draw the hydrogen, you don't have to, but there it is. That is your aldehyde functional group. Number 3, it says identify the functional group in each compound. An alcohol, an amine, etc. So all of these have an alkane functional group, which we're not going to write in. But for A, if you draw it out, you end up getting something like this. Or exactly this, I should say. This group at the end, this is a carboxylic acid functional group. That is it. For B, you can again draw it out. You're going to get something like this. Note the CH3s are on the same thing. They're connected to the same carbon. CH2, or CH3. So you should get something like this, or exactly this, actually. Over here, we have this functional group, the oxygen connected to the 2 carbons, or 2 carbon chains. This is what we call an ether. Moving on to C. Again, you can draw it out. CH3 is connected to this CH, which has the NH2 group. And then it's also connected to CH2, and then that's connected to CH3. So you should get this. Over here, this is the amine functional group. If you want to be very specific, this ends up being a primary amine. Just, it tells you how many carbons it's connected to. D, you have, if you draw it out, you get this. Nope, that's why you get this. This functional group here, where you have carbon connected to an oxygen. Sorry, double bonded to an oxygen, and then connected to an oxygen with a carbon group. This is called an ester. It has to be a carbon group. If it was a hydrogen, it would be a carboxylic acid. Going on to E, we're doing the same thing here. So this is what we drew up above. Over here, we have another functional group. The carbons are not required here. This functional group is called an amide. Because this amide is connected, or the nitrogen is connected to 3 carbons, we would call this a tertiary amide. I don't think you have to know this, but you want the specifics. F, you have this OH group. This is already drawn out for us. It's the only functional group here. This is an alcohol. And then G, it says draw any alkene, alkyne, phenol, aromatic alkyl halide. I will leave that up to you. I won't draw anything in here. 4 says classify the carbon atoms in a 2,4-dimethylpentane and ethyl cyclobutane as methyl, primary, secondary, tertiary, or quaternary. All right, so the first thing you want to do is draw these out. So for A, you have 2,4-dimethylpentane. So the first thing I like to do is start out with the parent chain. Pentane, so I know that this is 5 carbons. So I have 1, 2, 3, 4, 5. Just to double check. 1, 2, 3, 4, 5. Make sure you count your carbons. It's a very, very common mistake to have 1 more or 1 less. Now I'm going to go ahead and label them. You can go left to right, right to left. It does not matter. I'm going to label them from left to right. Now it says I have methyl groups on the 2 and 4 positions. So 2,4-dimethyl. So I draw my 2 methyl groups like that. I don't know why I drew a 4. That's a 2. And then I can go ahead and label these as primary. methyl, primary, secondary, tertiary, quaternary. So all of these classifications for methyl, primary, secondary, tertiary, and quaternary indicates how many carbons it's connected to. So if you have a carbon that is connected to one carbon, directly to one carbon, it's a primary carbon. If it's directly connected to two carbons, it's a secondary. If it's directly connected to 3 carbons, it's tertiary. Quaternary is 4. Methyl is 0 direct connections to a carbon, so something like an ether group. What we saw on the last page, you could consider this carbon a methyl carbon. But we're just going to do it based off of this classification. It's not too bad. This carbon down here is connected to one carbon. That's primary. The same thing here, and same thing here. These carbons in the middle, these are connected to 3 carbons directly. So those are tertiary. This carbon in the middle is connected to 2 carbons. So this is a secondary. That is it. Going on to B, we have ethyl cyclobutane. Drawing that out, we have cyclobutane as the parent chain. We can draw a square. We have an ethyl group hanging off of the first carbon, like that. Since the 1 is not put in, it's implied to be 1. So think of it as 1 ethyl cyclobutane. You can really put it wherever you want, as long as you denote that carbon as 1. Doing the same thing as we did before. This one is a primary. It's connected to 1 carbon, secondary, tertiary, secondary, secondary, and secondary. And that is it. It's not too hard. Not too bad at all. Number 5, it says name the following organic compounds. So for this one, the first thing you want to do is find the longest parent chain. So for naming these alkanes, you want to find the longest carbon chain. This is going to be your parent chain. So when you're counting these, I'm going to start from left to right. 1, 2, 3, 4. That's clearly not the longest chain, right? I could keep going. So that's not going to be the longest chain. 4, 5. That's also clearly not the longest chain. If I want to find the longest chain, I'm going to keep on going all the way to the bottom. 9, 10. So this is the longest parent chain. Now, once you find the longest parent chain, you're going to name it. So here, and keep in mind, this is the end of the name, of the full name of the molecule. So for A, this is a chain of 10. This is going to be decane. That's what it's going to end with. Now we go ahead and name substituents. And we name the substituents in such a way where the sum of their numbers is minimized. So what does that mean? So I'm going to go ahead and do this in 2 ways. I'm going to do it in the way I just wrote it, from 1 to 10, left to right, and then I'm going to reverse the chain. I'm going to go from 1 to 10 going the other way. So if I were to name it like this, this is, there's a methyl group on 3, there's a methyl group on 4, there's a methyl group on 7. So this is 3, 4, 7 trimethyldecaine. If I were to go the other way around, if I were to do 1, 2, 3, 4, 5, 6, 7, I missed one. Oops. Sorry, let me relabel that. 1, 2, 3, 4, 5, 6, 7. I missed another one. What is going on? 3, 4, 5, 6, 7, 8, 9, 10. There we go. Didn't miss any now. If I were to label it from right to left, and I were to name this, this would be, it would still end with a decane. It would end up being 4, 7, 8 trimethyl decane. Now, when I'm talking about minimizing the sum, you're looking at these numbers, the numbers for the alkane groups. This is only for alkanes. So for those of you who take OChem, again, when you start naming things with other functional groups, which is going to be the vast majority of your molecules, it's going to be a different rule for naming. So this is just for alkanes, only for alkanes, pure alkanes. Please keep that in mind. So if you're looking at the numbers here, we're looking to minimize the sum of these, right? The top one has a sum of 14. The bottom one has a sum of 14. Yeah, that's correct. 14. The bottom one has a sum of 19, right? So one is clearly a lot larger than the other. Because of this, this one is wrong. And the answer is this top one. Oops. Sum is not minimized. And that is it. Going on to the next one, we're going to follow the same rules here. You find the longest carbon chain, that is your parent chain. The longest chain here is 3. You could draw your 3 up here, it does not matter. Just drawing the one where it looks neatest, at least neatest to me. Then to name this, the chain is 3, so this is propane. And I have 2 methyl groups on the second one, so this is 2,2-dimethylpropane. And that is it for this one. Going on to the next, we have a ring here, this ring. So for that ring, this is going to be cyclo. It's a 3-membered ring. I almost put pentane. Cyclopropane, right? If I go ahead and I just label, again, I want to minimize the number when I'm adding them. So I'm going to want my substituents on lower numbers. So I'm going to want to start at one of the substituents, right? So I put 1 there, then I put 2 on the top one. You can go ahead and try the other names. I won't do it here, but you'll notice that doing this minimizes the sum, right? Switching the 2 and the 3 gives you a higher number than doing it like this. Again, I won't be doing it, but you can do that if you want to double check. So this is going to be 1,2-dimethyl cyclopropane. Going on to D, it says we have 1-ethyl 4-methyl. Oops, sorry. Reading the answer. So if we go ahead and label this, we have 1, 2, 3, 4, 5, 6, 7, 8. Or sorry, 7-membered ring. Now, if I go that way, my methyl group is on the 5th position. If I go the other way, 2, 3, 4, 5, 6, 7. My methyl's on the 4th position, so this will minimize the number. Now, the next question is, why did I pick ethyl before methyl? Because ethyl comes before methyl alphabetically. if I were to reverse the ethyl and methyl, right, the one on the 4, you end up getting the same numbered set, or the same sum, I should say. So here we go by alphabetical order. So the ethyl comes first. So naming this, we have an ethyl. So we have one ethyl, or you could just say ethyl. One ethyl, and then we have a methyl on the 4th position. One ethyl, 4 methyl. This is a ring, so we have cyclo. It's a ring of 7. This is heptane. Going on to number 6, it says, what is the major product expected from the monobromination of, excuse me, 2,2,3 trimethylpentane? So if I were to draw out 2,2,3 trimethylpentane, 1, 2, 3, 4, 5. Yep. And then it says I have 2, 2, 3 trimethyl. So you should get that molecule, right? Ordering 1, 2, 3, 4, 5. So for monobromination of 2,2,3 trimethylpentane, which carbon does it pick? You don't have to know this. I don't think this is covered in your lectures, but monobromination is typically done as a radical reaction. You don't have to know the mechanisms of these reactions. However, knowing a little background may help. So monobromination is what we call a radical reaction, or it forms a radical. More importantly, it forms a carbon radical. How this happens, you do not have to know. If you want to know, the bromines form a radical. To get enough energy from light, the bromine rips off a hydrogen from one of the carbons to give you HBr, and then you get a carbon radical. The reason I am mentioning this is that carbon radicals have different stabilities depending on whether they're methyl, primary, secondary, or tertiary. Can't be quaternary. You can't form a radical on a quaternary carbon. You would be violating the octet rule. But there's different stabilities associated with different carbon radicals. So with monobromination, the bromine prefers, I want to make this clear, prefers, so it doesn't always go on the carbon it prefers, just typically does. It prefers tertiary carbons over secondary carbons, over primary carbons, over methyl carbons. Again, the reason is that the carbon, and actually, let's just make this more general. Let's just say the reaction stability increases. That's not the correct way to say it. You could say reaction rate increases. Due to carbon radical stability. So a tertiary carbon is more stable than a secondary carbon, or tertiary carbon radical is more stable than a secondary carbon radical, which is more stable than a primary carbon radical. Again, you don't have to know those forms. It may help you remember it. I know it helps me remember it. So hopefully that helps. Those of you who take OChem, you will have to know this. But the reaction rate will increase going towards tertiary just because it's a more stable carbon. Quaternary carbons, they do not form radicals. So because it violates the octet rule. So the bromine does not go on a quaternary carbon. Um, yeah. All right, so then looking at this, if we were to pick the site of preference, right, which is the major product, um, that's the way you can think about it. Where does bromine prefer to go? Labeling these carbons, this is a primary, this is a quaternary, these are both primaries up here. This is a tertiary, this is a secondary, that is primary. As we just established, the bromine would like to go on the tertiary carbon. And then what happens is it replaces the hydrogen. Like that. That is it. If you want to know why stability increases, you can look up something called hyperconjugation. I will not be talking about that here. But it's cool. Easier than memorizing or more interesting. What is the major product expected from the monobromination of methyl cyclohexane? How many monobromination products are possible? Once again, I will draw this out. So I have a hexane ring like that, six-membered ring. I'm not going to go ahead and label this. I have a methyl group hanging off the first carbon, right? I'm not going to number this, but carbon number one would be that one. Labeling these as primary, secondary, tertiary. This is primary, secondary, 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 secondary. This is tertiary. We know the bromine wants to go onto the most substituted, excluding quaternary carbons. So it goes on the tertiary carbon, replacing that hydrogen that is not drawn in. That is it. You can draw the BR going up and down, it doesn't matter. Right, it's the same thing. Because I have not drawn wedges and dashes. Number 8, it says, draw the structure to represent the principal major product of each of the following reactions. So this is saying, I take something and I add HBr, and I get this. Now, for those of you who take OChem, there's going to be 2 reactions, at least that I can think of off the top of my head, that do this. For this class, you only need to know the addition reaction, where you have a double bond and you add this HBr and it gets rid of the double bond and you get the bromine going on there. We call this a Markovnikov rule in organic chemistry for addition reactions. I don't think that's something you have to know. Maybe it is. But if you see an HBr, you can assume that there's going to be a double bond somewhere for this class. The other one's a dehydration for those of you interested. It's an OH group. So if I need a double bond, then I'm going to get rid of, and bromine goes on one of them. I'm going to have something like this. Right, so that way when I add the HBr, the bromine can go on here. The double bond goes away. The hydrogen goes on the other. It is symmetric, the molecule, right? So wherever the bromine goes, you can just rotate this and you'll get this. But that is the answer here. If you add HBr, assume you're doing an addition reaction where essentially there is a double bond in the molecule. If you have to know Markovnikov's rule states that the hydrogen goes on the carbon with more hydrogens. So if I had like a methyl group here, then the hydrogen would go onto this one after the reaction, and the bromine would go here. So you would get that. Going on to B, we have this chain reacting with NaCN. If you have something called a leaving group, where a leaving group is something that is a good or a stable base. So something that can stabilize a negative charge. So Cl minus does, right? That's an ion in water. That's stabilizes it fine. So chlorine is a good leaving group. Iodine is a good leaving group. Bromine is. All the halogens are. I think those are all the ones that you will have to know. Water, OH2 plus is a good leaving group. I guess it's technically not water, but that's a good leaving group. I don't think you'll have to know other ones. You do have to know, however, that this CN group is what we call a strong nucleophile. So a nucleophile is something that typically has a negative charge. This NaCN, if you were to write it out in solution, you can write this as Na plus Cn minus. Yeah. Why is the Cn doing this reaction? I'll talk about the reverse reaction in a second, why it doesn't happen. I don't think this is something you have to learn or know, but the Cn is a strong nucleophile due to the negative charge. And the carbon can't stabilize it super well, so it wants to react with something. It wants to get rid of the negative charge, right? React with something to get rid of it. So what happens here is that the Cl and the Cn swap places. This is what we call an SN2 reaction. I am not talking about inversion of stereochemistry. I don't think that is something you will have to know. For those of you who take OChem, you will. But really, all that's happening here is we are switching those two groups out. I replace the Cl with Cn. Then I get a Cl minus. Now, if some of you may be thinking, well, I just said the Cn minus has a negative charge. Why doesn't the reverse reaction happen? The Cl minus is a lot more stable than the Cn minus. Why that is has to do with things like inductive effects, things that are outside of the scope of this class. So kind of just going to have to trust a reaction happens, right? I would assume that anything you're given, you can assume a reaction happens. All right. If there is a stereocenter on this last carbon, in case you need to know this, if there's a stereocenter and you have this SN2 reaction happen, it inverts the stereocenter. So if it was an R stereocenter, it typically turns into an S stereocenter. It typically has to do with reasons and like the naming of the canonical prelog, something like that. But it'll invert the stereocenter. So typically, if it's R, it turns into S. You can just read it like that. If you have wedges and dashes, let's say if the chlorine was on a dash, you would put the CN on a wedge, right? And that's another way to invert it. That's the physical inversion of it. Then you can figure out whether it's R or S. Usually it swaps. For number 9, it says identify the chiral carbon atom, if any, in the following compounds. So for a chiral carbon, you need 4 uniquely attached groups. This does also imply that you need a tetrahedral geometry. You can't have trigonal planar, you can't have linear, it has to be tetrahedral. So if you're looking at these carbons, that carbon has 3 hydrogens. I'm not going to draw them in, right? But we know there's hydrogens there. There's 2 hydrogens on this carbon, so neither of those can be chiral carbons because they don't have 4 unique groups. They're all the same. Or not all the same, but more than one is the same. Okay? One has 3 hydrogens, those are the same. One has 2. This one has 2 hydrogens, those are the same. What about this carbon? This carbon has this carbon chain over here. It has a hydrogen, then it has these 2 groups. It's not chiral because these are two methyl groups. That is the same, right? These methyls are not chiral for the same reasons. They have 3 hydrogens that are not drawn in. So it's not 4 unique groups. However, this carbon right in the middle is chiral. There is 4 unique groups here, right? There is an OH, there's an ethyl on the left, there is this T-butyl on the right, and then there's a hydrogen. That is 4 groups. Going on to number 2, this carbon down here is not unique. It has 3 hydrogens. The carbon in the middle has 4 unique groups. There's a hydrogen, there's an OH, there's a Cl, there's a methyl. Those are obviously different. Last one, this carbon over here is the only carbon we can really look at because these carbons cannot be chiral because they are like that, right? Those are trigonal planar. They cannot have 4 unique groups. They're only attached to 3 things. These are carboxylic acids. So the only carbon we have to really worry about is that one. We have 3 CO2H groups, or 3 of the same carboxylic acid. This is not chiral because they are not unique groups. And then I will make a note here. It's not chiral. It's not sp3 hybridized or trigonal planar. All right. Or it is trigonal planar, I should say. Going on to number 10, it says draw the name for alkanes and cycloalkanes for these isomers. Now I want to make a note here. The alkanes are with the C6H14. The cycloalkanes are with the C4H8. If you don't read it like that, you won't get this question correct. C6H14 is what has no degrees of saturation, which means that you can't have any rings or double bonds. Otherwise, if you do, you won't have the correct number of hydrogens. You may have the correct number of carbons, but you won't have the correct number of hydrogens. C4H8 has 1 degree of unsaturation, or it has 1 ring or 1 double bond. Here it's a ring from what they tell us. So please be careful on your test if something like this comes up. Test or quiz or whatever. So easiest isomer we can do for C6H14 is normal hexane. 1, 2, 3, 4, 5, 6. So this is your hexane. That is done. Now we can look at a 5-membered ring. Or 5-chain ring. Sorry. Why am I saying ring? A 5-length carbon chain. So this is a 6-chain. These are going to be 5 chains. There's only 1 6-chain. You have 6 carbons. So with a 5-chain, I have 1 carbon left over, which is a methyl group. I can't stick the methyl on at the end. That gives me the same thing I just had. So it has to go into one of these middle groups. So I could stick the methyl here, right? This would be 2-methylpentane, numbering from right to left, because you want to minimize the number, the sum of the numbers, right? From left to right, it would be 5 or 4, sorry. Another way you could do this is put the methyl in the middle. This is another isomer. This is 3-methylpentane. Putting the methyl on at the end here gives us 2-methylpentane again. So I'm not going to write that out. Now we can go on to move on to a 4-chain. So we have a butane parent chain. Now I have 2 carbons left over. So I can have an ethyl group. If you were to draw this and you were to say, this is 2-ethyl butane, you would be wrong, right? If I said this is 2-ethyl butane, this is wrong. Why is this wrong? Because now you're not following the normal naming conventions. How? Because now the longest parent chain is not 1, 2, 3, 4. The longest parent chain is 1, 2, 3, 4, 5. Right? Putting the 4 there would be wrong. And so if you were to name this, you would get 3-methyl pentane, which is the same as up above. So don't make that mistake. Very easy one to make. Moving the ethyl down to carbon 2 instead of 3 gives you the same thing. Sticking with the 4 parent chain, you can have 2 methyl groups. 2 methyls or 1 ethyl. This is clearly a different group. If I were to name this one with the 2 methyls there, this would be 2,2 dimethylbutane. And then I can also have the methyl groups on 2 different carbons. And this would be 2,3 dimethylbutane. Then that's it. Going on to a 3 chain, you can only stick stuff on the middle one, and you end up getting the same molecules that we've already had. So I won't draw those out. Now we can move on to C4H8. So we know that this is going to be a ring, right? There's a ring of 4. There's only one way to draw that. That's cyclobutane, like that. Then we can also draw a 3-membered ring. You can draw a methyl group. This is 1-methyl cyclopropane. I'm not going to put the 1. That's all you can draw. You can't have a 2-membered ring. Again, you can have alkenes here. They do just ask us for cycloalkanes, so we're not going to draw them. Moving on to number 11, and the last one, it says, identify whether the following molecules could be chiral. Also designate the molecule as R, S, or neither. So what we're doing here is, again, looking for a chiral carbon. This carbon is connected to 4 unique things, as we kind of went through before. I won't be going over that again. It is chiral. So CH4. Now what do you do? Right? How do you do this? So this is a yes, but how do you do the designation, whether it's R or S? I'm going to go ahead and draw this out very explicitly. Make this very clear. So that is the molecule in question, drawn with all the hydrogens and the carbons. What we're using here is the Kahn-Ingold Prelog to label this as R or S. So how do you do it? You go based off of atomic number. So for designating stuff, you give priority or priorities to groups based off of atomic number. So looking here, this is the carbon in question that we're looking at. Fluorine has the highest atomic number. This one clearly gets a priority of 1. So that's 1. Hydrogen is the lowest between fluorine and these 2 carbons that it's connected to. So that's 4. We have 4 things, priorities 1 through 4. Then we have to look at the 2 carbons. Well, carbon has the same atomic number as carbons. What do? You look at what the carbons are connected to. So if 2 groups have the same number, check the groups they are connected to. They are connected to. And choose the one connected to a higher atomic number. So if we're looking at this carbon, this carbon is connected to a hydrogen, a hydrogen, and a hydrogen. You also could consider this carbon here. Keep in mind that both of these, we're comparing these 2 carbons. They're both connected to the same carbon. So it doesn't really make too much sense to compare it, but you can if you would like make this very concrete for yourself. Like looking at every single group, I guess. But this carbon is connected to 3 hydrogens and let's say a carbon. So it has atomic numbers of 1, 1, 1, and 12, right? Looking at the carbon it's connected to. Typically, I don't do this, but I want to make it very clear. Looking at that carbon. For this carbon over here, it has hydrogen, hydrogen, carbon, carbon, right? So it's connected to, and actually, higher atomic numbers. So it's connected to 2 12s, right? Carbon has an atomic number of 12 and 2 1s. So this carbon ends up winning. If you don't look at the carbon that they are connected to, it's more clear, right? This one would be connected to 3 1s. This one is connected to 2 1s and a 12. So this one wins. So that one gets priority. This one is a priority of 2. That one's a 3. Then after you figure this out, if priorities go clockwise, give S, or sorry, give R designation for now, not completely. If counterclockwise, give the S designation. Now 3, and this is the important thing, is if the lowest priority is not on a dash, then you want to flip the designation. So if you had R, then you would get S, right? So really in this case, we're looking at hydrogen is on the lowest priority. It's not, so we're gonna have to flip it. That's our 4th priority. 4th is lowest, by the way. So you can see here that this is going clockwise. So this is R. But then you can see that 4 is not on a dash. So we flip this to S. So the designation for this first one is S. Again, we flip it because the lowest priority is not on a dash, it's on a wedge. Doing the same thing for the second one, this is the carbon that we're looking at, whether it's chiral or not. Doing the priorities on this, oxygen has top priority. There is a hydrogen here that is on a dash. This gets the last priority. This group over here gets second. That methyl group gets third. One is connected to an oxygen. The other is connected to 3 hydrogens. The one connected to the higher atomic numbers wins. So that's that group, right? That CH2 group. So this is chiral. And then if you're looking at this, this is moving in a counterclockwise direction from 1 to 2. That's really what you're looking at. So from 1 to 2 to 3, that goes counterclockwise. This is S. That is it for this worksheet. I hope that helps, and best of luck on your test.